Okay, so anyway, I twist this bond around to have this position of the oxygen so that it is within reach of the carbon. So in the process, I form a bond with the, so carbon and oxygen will have a bond. Hydrogen will transfer to this oxygen. So you have a cyclic hemiacetal. So the straight chain glucose molecule can form a hemiacetal as well. Okay, so that you will follow, I'll just label this properly, the carbons. So this is carbon 1. You have carbon 2 here. Carbon 3. Carbon 4. Carbon 5. Carbon 6. So when I push it down, tilt it towards the right, so move it in the clockwise direction. So this will be carbon 1, this will be carbon 2. This will be carbon 3. This will be carbon 4. This will be carbon 5. This will be carbon 6. Okay. So what will happen is, so once I twist this into horizontal form, so I can bend the structures around. So I will form this circle, this cyclic structure. Okay, so this is carbon 1, this is carbon 2. This is carbon 3. This is carbon 4. This is carbon 5. This is carbon 6. So if you notice, if I rotate it clockwise, all the groups on the right here will be the ones at the bottom. So all the groups on the left will be on top. Okay, so the H group carbon number 2, the OH will be here. H will be here for 3. OH will be here at the bottom for carbon 4. Okay, for carbon 5, so this is one has to be explained better. So for carbon 5, you would expect that the OH is found here. However, if the OH is found here, then the CH2OH will be found in this part. But if you put the carbon here, instead of a 6-membered ring, you will have a 7-membered ring, which is not stable. Okay? So what I will do is I will twist it around along carbon 5 so that the CH2OH is found on top. Eventually, it will bring the oxygen within striking distance to the carbon 1. And then the H will be found at the bottom. Okay, so that's the main confusion of students. Why is the H downwards? Okay. So when that happens, the oxygen is now in a position to combine with to form a bond with carbon 1. Okay. So once it forms a bond with carbon 1, what will happen is the carbon 1 will become chiral. So when that happens, this carbon 1 will have 4 different groups attached to it. You have H on top. Well, depends. You have HOH, oxygen, and another group. So this becomes chiral. So when that happens, there's stereoisomerism involved, meaning the positioning of the H and the OH group can be different according to it can be two enantiomers. So in the process, we call it the different positioning of these groups. We call them anomers. So the position of the H and the OH can be different. So if the H is found on top, it's called alpha. If the OH is found in the at the top, it's beta anomer. Okay, so this is alpha D glucose. This is beta D glucose. So how do you differentiate between alpha and beta? Again, the H is found on top for alpha. For beta, the OH is found on top. So I use the mnemonic abo. Okay, so that helps me remember that when it's alpha, the H is on top. When it's beta, the OH is on top. Hirap intindihin, no? Okay, so it's difficult to understand. Anyway, so I'll give you another video to to get the sense of it. So hopefully you will follow what I have understood, what I have taught you. Any questions at this point? Okay, no questions. So it's been, you got it. So the structure that you saw here, the cyclic structure is called the Hayward structure. Yes, Jeremiah.
Prof, question lang po doon sa may anomeric carbon po. Bakit po may OH dun sa dulo po?
Yun nga, kasi nga
Hindi, sa kaliwa.
kaliwa.
Opo. Yung sa may more stable form po. Yung ginawang, ayan po,
Bakit may OH saan?
sa may after po ng 6.
This is carbon 5 eh. May OH talaga yung carbon 5. Ito, this is carbon 5. So, are you talking about this OH? So, carbon 5, ito yung OH niya. Ito yung OH niya. Ay, sorry, mali. Ito pala yung carbon 5. Mali. Clear. So, ito yung carbon 5, di ba? So, ito yung OH niya. Ito yung OH niya. Okay, nasa baba H. Nasa taas H2OH, which is this one. The H2OH here is here. And then the H is found here.
Okay po, thank you
As
po.
I said, I twisted it around, no, so that the oxygen of the fifth carbon is within striking distance, so that it can form a bond with the first carbon. So oxygen is part of the ring. Okay, hopefully that clears. Is that clear? Is it clear?
Yes po, thank you po.
Okay, going down. Okay, so the fifth carbon, the OH, this group is within striking distance of the carbon here. So the oxygen that's in the red, this is the oxygen it is pertaining to. So the oxygen is within striking distance to form a bond with this one. So the H is removed, becomes part of this. The H will become part of. It will become part of this, so that you have OH. Okay. Okay. So again, the OH in carbon 5 is just the right distance away from the carbonyl to form the six-membered ring. With oxygen, it's part of that ring. Okay, so the positioning, these are implicit hydrogens. The hydrogens here are implicit. So you have the hydrogen here on top. And you have the hydrogen here in the bottom. Okay, so you look at the positioning of the H's. The carbon 2, the H is on top. The H is on bottom for carbon 3. Carbon 4, the H is on top. Okay, so for alpha D glucose, H will be found on top. For beta D glucose, the OH is found on top in the cyclic structure. So that's the most important structure you have to recall. For fructose, this cyclic structure can also occur, but this time it's a five-membered ring. So the oxygen on carbon 5 will still form a ring, but this time it will be a five-membered ring. So instead of if we're focusing on the H in glucose, now it will be CH2OH. So the alpha positioning of the CH2OH will be on top. For beta, the OH is found on top. So what is the consequence of this alpha and beta anomers? So earlier we discussed cellulose has a different positioning of the bonds between the glucose. Okay, so do you have an idea? Do you have an idea why we cannot digest paper or grass? Does anyone have an idea? Yes, Jeremiah?
Kasi wala po tayong enzyme na nagda-digest nung papers.
Yes. So basically, the positioning of the attachment of the glucose units in cellulose is different. So we don't have the enzymes to break it down. So um, starch in bread, in pasta, we can break it down using the amylase. So that's the way we can digest starch. But for cellulose, the attachment of the glucose units are in the beta position. So there we have no enzymes for that. Cows and other similar mammals who can chew a cud, I mean, they can put the grass that they eat into another separate compartment in their digestive system, and then they can bring it out later for more thorough chewing. So those mammals, they have bacteria in their digestive system which breaks down these the structures. Okay, termites also have these enzymes in their digestive system. So we humans do not have beta amylase, so we cannot digest cellulose, such as wood or paper. But it does not mean it's bad. Um, the reason why we eat fiber, so when we say fiber, it's the undigested portion of food. So that's made up of cellulose. So whenever we eat vegetables, the leafy vegetables, of course we cannot consume it. But the fiber there, it helps in our digestive system because it slows down the absorption of the food into our small intestines. And as it goes into the large intestine, so it helps clean our digestive system. No? So it helps make our stool more soft for so that you won't experience constipation. So when you lack water and vegetables and exercise, the tendency is you will have hard stool. So you'll have constipation. It's hard to defecate. Okay, so it's a good idea to eat vegetables because it will help you in your digestive system, even though you cannot digest the cellulose. Okay, so this is the fiber. So by the way, the structures, the Hayward structures here, you have beta D glucose and alpha D glucose. They can uh, transform into one another. So conformational, meaning they can change positions. So this is what you call uh, mut- mutarotation. So change in specific rotation that accompanies the equilibration of the alpha and beta anomers in aqueous solutions. So 64% will have this anomer, but it can have an open chain form, only 0.02%, and then by attachment, you'll have another form, alpha D glucose. So that's about 36% of the one found in solution. Okay, sorry if I said conformation. So we're talking about the anomers. Okay, so the position of the anomers, you have beta here, and then you have alpha there. So in solution, 64% is beta D glucose form. And you have 36% is in the alpha D glucose form. Okay, so another important aspect is that this you have a lot of bulky structures, bulky atoms or group of atoms in the cyclic structure. They may push each other away. Okay, so this is where conformation comes in. So this molecule itself will position itself in such a way that they will it will form a new structure, not that a new structure, sorry, a new conformation, such that some of the bonds will be pushed up and pushed down. So in this, the carbon 4 can have a more comfortable position, quote unquote, if it's pushed up. So like this will become like the backrest of a chair. And then carbon 3 will be pushed down. So this will become like the leg rest of a chair. So hopefully you can see the image of a chair from this one. So the positioning of the group, so let me guide you through it. So for carbon 2, carbon 1, let's go to carbon 1 first. So carbon 1, since the H is down, H will be positioned down, and the OH will be found in what you call the equatorial position. Okay. So in order to know which one is axial and which is the equatorial, let's start with the H on carbon 1. So the positions of the H will be axial from this point. So H is found here, going down. Okay, H, that's H and H bond. So alternate the up here. Carbon 2 will be, the position of the H will be up. Carbon 3, the position of the H will be down. Carbon 4, the position of H will be up. Carbon 5, the position of H will be down. So alternating, starting from carbon 1. If we're looking at the beta conformation, so H, carbon 1 is down. Carbon 2, H is up. Carbon 3, H is down. Carbon 4, H is up. Carbon 5, H is down. So these are what you call the axial positions. And this is more stable because the H is a small atom. And the axial positions create too much steric hindrance. I mean, if the groups are positioned in the axial positions, they push each other. So it's like in an uncomfortable position. Okay. If we talk about it scientifically, we're saying thermodynamically it's not stable because of the steric hindrance. Okay. So since the H occupies the axial positions, the OH groups are found in the equatorial, what we call the equatorial positions. So this is ideal because OH is a large group. The equatorial positions occupy, the equatorial positions give more space for them. So this is ideal for their, what we call the less steric hindrance, or quote unquote, they're in a more comfortable position. Okay, so to help you visualize what that looks like, so I'll go back to okay, we have here a structure of cyclohexane, but instead of but this is the structure that is most similar to glucose. So let's just visualize which one is which. So the oxygen is found here. This one is oxygen. Anyway, I have 1 minute left, so I guess I'll just show you a video first, and then I'll give this explanation later because we have 1 minute left. So I'll give you another link to another video.